As I said during the introduction, I'm neither a researcher from optics, neither a researcher or no researcher from ultrasound. So I'm a bit on the side. I'm the kind of ovni here. But anyway, I'm going to try to explain you first another imaging modality, since it's a teaching course on the part of imaging and bioimaging. So MRI is one of the major methods for which is widely used in the clinics. So I will first start with explaining you how MRI works, because I don't know if all of you have any idea of how it works. I will try to explain this a bit by hands and also with some equations. And you will see this is highly linked with Fourier. And then I will go in showing you what you can do with MR and coupling MR with ultrasound. So the general context is, I've been working for almost 15 years about the idea of trying to fight against cancer, and the idea is to try to destroy a tumor, which is shown here in yellow. And this tumor is of course surrounded by healthy tissue that ideally you have to preserve. So there are a number of methods, more or less invasive, that you can use, and you have also the idea to try to burn the tumor by increasing the temperature, ideally inside that region, and trying to protect the surrounding tissue. And to induce this temperature increase, you have a number of methods which can be invasive, such as microwave, laser, radiofrequency, but also non-invasive methods using focused ultrasound, high-intensity focused ultrasound. Whatever the method is used for inducing the temperature change in that pathologic tissue, the idea is what's the actual temperature distribution inside my tissue during the treatment. So the idea there is to use magnetic resonance imaging to try to map in real time the temperature change, the temperature distribution into my tissue while I'm trying to treat my tumor. Okay, and this temperature distribution here and the surrounding tissue depends on the tissue properties relative to temperature, namely the thermal diffusivity, the perfusion of the tissue, and the temperature at the interfaces between the different tissues. So let's start with MR. You can see on this slide some typical images that you can get with a standard MRI scanner that is used daily in a clinic. So it's a sagittal image of the head, where I can clearly see the brain. This is a transverse image of the abdomen, where you can see the liver. And these are kinetic movies where you can clearly see the heart contracting. This is the left ventricle, the right ventricle. These are the two atria. And you can clearly see here the valve that you have just seen before in the ultrasound image from my colleague. The nice thing with MR is that it's operator independent, and you can make images in any orientation in space as you want. So the question is, how does this work? And once I will try to explain you how it works, then I will show you some examples of how we can use it for monitoring the therapy. So basics of MRI, I'm not going to enter too deep into the details, but basically what we are looking at is that we are dealing with the magnetic properties of the spin, the kinetic moment, or the magnetic moment of the protons of a water molecule. Okay? So what we are making images of is images of the water through these magnetic properties. So this is a big magnifying glass. And when I put this magnetic moment into a strong static magnetic field, for example, putting the patient inside this magnet, this is the direction of this important magnetic field, then all of this magnetic moment will align. We're not going to change the orientation of the molecule itself. They're going to stay in the normal state, simply that the magnetic moment are going to align with B naught. Okay. As a consequence, you can get a net macroscopic magnetization, which is simply the sum of all the individual small magnets that have been aligned by the strong magnetic static field. Okay? And you get this equilibrium state of this magnetization. And as always in physics, once you have created an equilibrium, what we're going to do is to kick it, to disturb this equilibrium state and look at how it comes back to its initial position. So how does it work? Well, how to kick this magnetization? Well, to move a magnetization, you can apply a perpendicular oscillating magnetic field, which is called B1, and you bring energy into your system, and this is going to make this magnetization, which is gently aligned with this B0, to rotate, for example, by 90 degrees, and to become perpendicular to this B0. And then you stop this excitation, and you look at the relaxation of the system, which is going to emit some energy. And this energy is going to be recorded with a detector or with detectors. You can use several ones. And then it's going to be, during the process of this small magnetization, to come back to its initial position. The tricky thing is that it's not like a standard magnet. We can go into deep quantum mechanics, but I'm not going to do that. And it's more with try to explain this with hands. Technically, you can show that this magnetization returns to its initial state by making a 3D precession motion around B0. What does it mean? Sorry, I think it's not. This means that this magnetization that I have shown here, for example, a line here, is going not to flip directly, but it's going to make a spiral motion around B0, okay, and gently return to its initial position. What you can detect, so you can decompose this motion in motion into the transverse plane, which is this plane XY, and it's finally nothing more than a spiral in this plane. And in this axis, it's a recovery of the signal starting from 0 when it's perpendicular to its maximal value. Okay? So, what you can show, if you want more details, there are tons of articles and books explaining that. You can measure in the transverse place the magnetization, which is the amplitude modulated by this frequency. You have a motion around B0, which is proportional to this frequency. And then you have an exponential decay in amplitude, which depends on a specific time, which is called the transverse relaxation time, which is tissue specific. The T2 is different on the brain as compared to the T2 on the liver or any organ. Okay. And the magnetization along the z-axis returns progressively aligned with B0 with following this equation. And here you have a second relaxation time, which is called the T1. So you have, in fact, two relaxation times that are involved in the relaxation process. And what you measure is the transverse magnetization, because you have this magnet, this small magnetization turning, and you have a coil, and you can detect this, the flux of this moving magnetization. So some basic things, this precession, the speed at which it turns, is directly linear to the magnetic field, the static magnetic field that you're applying. This is a constant, this is called the gyromagnetic ratio. This is dependent on the nucleus. For a proton, this is the value. So if you put, for example, a B0 1.5 Tesla, which is the most common value for standard clinical MRI scanners, then you end up with a frequency of mutation which is 64 megahertz, and then it's fixed. Okay. So this is standard NMR experiments. But what I want to do is to make an image. Making an image is nothing more than being able to discriminate the signal that comes from, for example, this left arm, from the right arm, and from these different regions within that direction, for example. Well, as I said before, what we are going to do is to disturb the magnetization by putting a small B1, which is perpendicular to B0. Then, if I plot the signal in the transverse plane after stopping this B1, I get my relaxation from the blue part. For example, I get that amplitude because I have less water in that region as compared to that. This one has more water, so the signal is more intense. This one, again, has more water, so it's a bit more intense. And this one has intermediate value, so it's a bit less intense. And they all oscillate gently at the same frequency. And what you record with a single coil with simply a loop, and you cut the loop and you simply sample the electrical signal that comes from the magnetization flux that oscillates for all this, and you make the sum of that. It's completely different to what you do with ultrasound when you push and then you listen with plenty of detectors. Here you don't make any difference. You distort everyone and you listen the signal, which is the sum of everyone, with a single detector. This is temporal signal. Then if you make a Fourier transformation, then of course you get a spectrum. And you get a spectrum for this part, for each part you get a spectrum, and the intensities directly related to relative intensities that you get, which is linked with the water content in each part. And then of course what we get, since it's a sum, you get a single peak, which is the sum of all these peaks. Up to now, I have no way to distinguish from this signal what's happening here as compared to what's happening there. I have not made any profile, any image. But what I said before is that the precession frequency, the speed at which it's turning around B0, is proportional to B0. So now if I have a seldon coil around there, and I make a current flowing in one direction here and the current flowing in the opposite direction, I'm going to create a gradient of static magnetic field. If I create a gradient, I can express the frequency, which is now becomes a function of the position. Okay. If now I make exactly the same experiment, and then what's happening? This part has, for example, a lower frequency as compared to that part, because it does not see the same effective net magnetic field. Then the frequency is higher in that part, slower, slower, and slower. And still I get the sum of that. I can make the Fourier transformation of all these signals, but I don't get the information of all these signals individually. I simply make one measurement, which is the sum of that. Simply, this view by Fourier transformations simply says that these signals in blue appears in the lower frequency, this one a bit higher in frequency, etc., etc. And then, since I get the sum, by making the Fourier transformation of my signal, I simply get a profile, and I'm able to discriminate what's happening here as compared to there. Okay, that's the basic idea of MR. The spatial resolution is only dealing with the slope of this gradient, which tells you how much you separate between position versus frequencies. Okay, so a bit of mathematics. If I have no gradient, the signal I get is simply the sum over all the magnetization over X, this is my profile, which oscillate at the same frequency, and you have the exponential decay depending on your tissue type. And I have nothing to do with that. Now if my gradient is different from 0, then I get this expression. This depends on the X. It's a sum over X. This does not, so I can put them outside from the summation. And then what you get is simply the sum of your magnetization as a function of X multiplied by the term, phase term. And if you make a change of variable calling this Kx following that value, then you can simply modify or rewrite this S over time as S over Kx, which is this value, which is nothing more than the Fourier transformation of my profile. Okay, so simply by my signal that I measure, I make the Fourier transformation back, and I get my profile. This is the idea of MRI. This is from 1D, but then you can do it in 2D, for example. Now, instead of having one Kx line, I need to have a plane, which I can call the K-space, which is absolutely identical to what the previous speaker has shown. And here the difference is that now we are going to scan all the different lines in my K-space, and we're going to measure that, and once I get all these, I can Fourier transformation back in both directions, and I will get my image. Okay? So technically how do we do? We are at the equilibrium, then we put this B1, so we make a kick in our magnetization to put it in transverse plane to get signals to collect, and then at that time, since I have no gradient in neither in X or Y direction, I'm in the center of my K-space. Okay. Then, if I apply a gradient again the X direction, which is negative, then I will shift in position from here to there. The distance from which I shift depends on the surface of that, which is simply the product of the amplitude by the gradient, which is nothing more than the amplitude by the duration. Okay. So I'm here. Now I want to jump from here to there. Then it's simple. I simply have to put a positive gradient, and the surface has to be adapted to jump from here to there. And then I can sample the value of the signal, and I have my first point in my K-space. Then I continue. I simply put a second gradient, and then I move from here to there, okay? And then I can measure the signal here, and I have my second value in my K-space. And then I continue, and I can add several gradients and read in between, and then I can read a full line of my K-space. Okay, I'm going to repeat this experiment. So second excitation, okay, same value here to move from here to there. Then I'm going to put this gradient a bit lower in amplitude. For example, the mass surface is going to be lower. So I will not move from here to there, but from here to here. And I will repeat this scheme, and then move, and again, acquire my second line. And then I'm going to repeat until I've covered all the lines I want in my K-space. Once I've done that, make a Fourier transformation in X and Y, and then I get a complex image because I've got the magnetization, the measurement in complex value. Then again, I can map the amplitude of the signal, the magnitude here, which is usually exploited day to day for in the radiology department for diagnosis. But you also get the map, a second value, which is the phase image, which is very analog, very close to what we have seen in this morning talk about holography. But here the difference is that we have access to the magnitude and the phase of the signal because we measure the complex signal. Okay? And this phase is nothing more than a map of the frequency. Okay, so I have a map of the frequency. Okay, that's it. But now we are 3D objects. So the question is that I want to make a slice in my patient because I want to make an image of the slice. How do I make a slice? Same idea. I put a gradient, for example, on the Z direction. This is the center of my magnet. My reference B0 gives me the exact value of my normal value of the frequency. Then I want to, with this gradient, I want to excitate, let's say, a region in frequency that is between omega 1 and omega 2. Ideally, if I want to cut this with a Heaviside function, I need to make a Heaviside function in frequency. Then, if I make a Fourier transformation back, I'm having then a sinc function in time. So simply, instead of making a B1, which is a Heaviside function, I simply put a B1, which has an envelope of a sinc, simultaneous to this gradient, and so I can put the magnetization of all the spins that are in this slice in the transverse place. All the other ones remain aligned with B0. And then I'm going to play reading all the lines of my K-space, one after the other. And that's the basic principle of making an MR image. I hope you're not lost completely. Is that clear?
Yeah, I wanted to know what is the value of the magnetic field in each situation.
This really depends on your instrumentation. The B0 clinical value, the standard clinical values are 1.5 Tesla and 3 Tesla. These are the most common clinical values. You have now initiatives to have higher and higher magnets, mainly for brain imaging, with the idea is that if you increase the magnetic field strength, you also increase the signal you can get. If you increase the signal, you can convert it into reducing the pixel size to get a better spatial resolution. Okay, so, and the spatial resolution depends on the gradient amplitude that you get. So it's typically depends on your hardware and the amount of money you are able to put inside. Okay, so this is the way that you select the slice and you encode the K-space. We are measuring the image in the K-space, and then we make the Fourier transformation back to get the image. Now, second point is that this is simply the way to do that, but I can put, for example, this is reading a line. This is jumping from one line to the other. I can put this very compact, as close as possible to my excitation. Then my signal is going to be maximum, because after I put my magnetization transverse plane, it's going to decay my exponential decay, depending on my T2. If everything is really compact here as close as possible, my echo time is going to be very short. So I have no contrast for tissue which have a very different T2, because you have maximum signals for both. But if then I shift in time the reading of this line, for example, then if I have two tissue, one which is relaxing very gently, slowly, I will get signal there. And if I have just on the side of this one, a second tissue that relaxes very fast, okay, then I will get only the signal of my first tissue. This is the way of doing contrast. So simply by changing the timing of reading that, you make the contrast, which depends on the T2. Okay. Now the second point is that I need to repeat this experiment to read lines by lines. But if I leave enough time between these two excitations for my magnetization to recover, to gently come back to its initial value along B0, then I can, during my second excitation, have all my signal coming back into my transverse plane, and it's going to make this precession and coming back. Okay. So I get all the signal available. But I can also reduce this delay, it's called the repetition time, and then if I reduce this time, I don't leave enough time for my magnetization to recover, so I'm going to saturate my signal, I'm going to reduce my signal. So by simply changing the timing of my echo time and my repetition time, make a contrast which is dependent on the T2 of the tissue or on the T1 of the tissue. If my echo time is very short and my TR is very long, the only contrast depends on the quantity of water. It is proton density. If my echo time is long and my TR is long, it's a T2 contrast. If my TR is long and my TE is long and my TR is short, it's a mix between a T2 contrast and a T1 contrast. And you can really adjust the contrast depending on the species you want to image. And this is the main force of the MRIs, that you can modulate the contrast by simply changing the timing of your segments. Okay. And of course, I put X, Y, Z there, but if you make 50% of this gradient on this axis and this axis, you're going to tilt your slice by 55 degrees in between X and Z degrees. So you can also, by simply changing the relative value of all these gradients on the physical axis, you can make an image with any slice orientation. Okay? This is what I would like you to remember or to understand, is that MRI is done by simply playing with the magnetic properties of the moment of the nucleus, the proton. And it's the only thing that we have in MRI is pulses, gradients, and timings. Nothing more. Okay? But with this, as you can do as many pulses, timings, and gradients in any direction that we want, we can do plenty of different contrasts. Okay, so come back to what I wanted to show you.
How well are those grids defined?
Sorry?
How well those grids, these K, are defined? How small?
I don't understand the question, I'm sorry.
The grid that you make for the K space,
yes,
right? How well they are defined, how well they can be resolved.
That's
to
a good
some
point.
extent, you come to the partial volume.
That's a good point. Usually, when I'm in front of a magnet, I don't say to my magnet, scan this value of the K space. What I want at some point is a field of view and a spatial resolution. So in front of your acquisition console, you define your field of view, which can be different in vertical and horizontal directions. If it's different, then it's going to have an impact on which point you have to read between the K space. And I'm going to define the pixel size. Since these are, I don't know if it's reciproc spaces, you can demonstrate that the smallest distance in the K space is inversely proportional to the largest distance in your image plane. So the distance in between these 2 points is inversely proportional to your field of view. If I want to make a rectangular field of view, this one is smaller than that one, which means this one is smaller, so the space in between the 2 lines there is going to be larger than the distance between 2 points. Okay? Then when I define, the distance in between 2 points defines my field of view, but then the pixel is also the smallest dimension in my image, which is inversely proportional to the largest dimension in my K space. This is the largest dimension of my K space. If I want to make a pixel which is twice smaller with the same field of view, I need to scan twice the distance. Okay, so technically, I give the field of view and spatial resolution, and the machine computes which K space I should use, and then, depending on the sequence I'm using, is going to adapt the gradient. Yes?
Can you repeat what the phase image shows? Because from my understanding, the phase would just be changed by the initial by the phase gradient. So there would just be a change of the initial phase, and then that would just be linearly
The phase,
increasing.
the gradient changes the phase over my object, and I acquire the sum of all magnetization with different phases.
Yeah, exactly.
So in the K space, the maximum signal intensity I will get will be in the center where I have no dephasing. Okay? If now I come very far from the center, an extreme point, I have a strong dephasing gradient in one direction, a strong dephasing region, but I'm still making the sum of the vector of all these vectors with different orientations. So I have very small signal to noise. Okay, so most of the signal is there, but here you still get information. Does this answer your question?
I know my question was, what does the phase image show that you have on the right top there?
The phase image, after Fourier transformation, okay, after Fourier transformation you get images, and these images, each pixel represents the net magnetization for the corresponding voxel. Okay. This magnetization has a direction, a length. This length, it's written in the context space. We simply use this real and imaginary part because it's convenient to use all the mathematics and of the context space. And then you can, in this pixel, the intensity is directly proportional to the length of the number of water I have inside. Here I have no water. My signal, the magnitude will be 0. My phase is not going to be defined. I will get no nuclear value of phase. But once I have this magnetization for each pixel, then the phase is defined. It's simply the angle at which it's turned. Clear or not?
Not 100%.
He is asking what does it signify?
I'm sorry?
What does it signify? Like the magnitude signifies, okay, there is a contrast of volume molecules.
The question is, why does it dephase?
No, yeah, what is the phase? Means what information I can gather from the phase. From magnitude, I can see the contrast of the material.
On the phase, there are plenty of things. The phase, if you have an ideal magnet with exactly the same value of the magnetic field everywhere, normally when you bring all the magnetization from the left to the right in the transverse plane, they should oscillate exactly the same frequency. The problem is that when you put a human body inside a static magnetic field, it's going to distort a bit this magnetic field. This means that when I'm in the magnet, the field that I have here and here is slightly different. Since the speed, the frequency of rotation depends on this magnetic field, I will get a slight difference in between. And this is why I don't have necessarily exactly the same phase here and there. So in this example, it's simply the difference in, this is a map of the homogeneity of my magnet. Okay, so you can do all these kind of images, and what I'm working on is really coupling MRI, because you can have excellent image quality, with therapeutic ultrasound. I'm not doing ultrasound imaging, but I'm sending a lot of power to try to increase the temperature inside my patient. What we are using is an array of transducer. Each of them can send quite a lot of power, and the idea is, of course, to focus the energy at the focal point, and then to use this to make a modification of the tissue. Okay, and of course, since we have a map, a network of transducer, by changing the phase in between all the elements, you can steer the focal point in any direction. Okay. This image is going to show you an example. In this image, I put one slice perpendicular to that, one below at the focal point, and one above. So you have 1, 2, and 3 slices, and I'm going to steer the focal point in 4 positions. Okay. If I'm perpendicular and I'm showing these images, I'm going to make 1, 2, 3, 4, 1 to steer the focal points iteratively like that. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And I'm going to show you images that we can acquire there. And I'm going to explain you afterwards what's that. So with MRI, you can map temperature change that's associated with the steering of the focal point. So the focal point in this experiment is moving from 1, 2, 3, 4, 1, 2, 3, 4. I am continuously steering this focal point to induce a temperature change that you can map with MRI. And to answer your question, in fact, the temperature change is included into the phase image. Okay. And this is what we're exploiting. So I'm going to show you this afterwards. And the interest of that is that you can repeat again. So you have 4 points, and doing this, you can then treat or burn a tissue which is larger as compared to the initial points, as if I was treating one after the other. So I take advantage of the temperature diffusion in tissue to treat a larger region, as if I was doing point-by-point treatment. So how does it work? What's the idea? Is that we're making a movie with our MRI. So we acquire sequentially images. So we get at the same time magnitude and phase images. We make a computation in real time on these images to make a monitoring, to simply look at the temperature change. And then if you, what I will show at the end of this presentation, using this, if you are fast enough and really in real time, you can then interact with your heating device and make a feedback loop. And you can control your energy deposition. And then your MRI is nothing more than a very expensive thermometry. Okay? So why do you want to do that? It's not because we have an MRI scanner and we have some spare time. It's because if you're able to monitor the temperature change in tissue, I mean in space and time, then as a function of time, you can plot the temperature change in its pixels, for example, following these curves. And then you can, for example, integrate the thermal energy that you have put in that pixels and use this metric and compute a kind of accumulated dose. This is called the thermal dose. And you can use this as a metric for predicting that you have effectively deposited enough energy into your pixel and that you consider this pixel is burnt. Okay, so I want to destroy this tissue. How does it work? So the question of what's information in the phase? The phase is nothing more than a map of the angle of magnetization. In fact, the frequency, this frequency of precession, is dependent on the magnetic field. That is also varying with temperature. And it's very slowly varying. It's 0.01 ppm per degree, it's very low. But then, if I have a change, if I compare the phase that I acquire prior to heating with the phase that I acquire during heating, you can clearly see a contrast in the phase, and by subtracting the two images, I can get a nice phase image that's only dependent on my temperature change. And then by knowing the correspondence between the temperature change and the change in the phase, I can simply compute a map of the variation of my temperature. This is the idea. Yes?
So the temperature changes the signal that we measure, but when you burn a tissue, it changes of properties, and the change of properties has an impact too on the
It may have an
signal
impact. There are several parameters that influence the contrast of the MR images that are temperature dependent. For example, the T1 is changing also with temperature. So if you're making an image which is highly weighted with the T1, you're going to change on your magnitude image, you're going to change, you see a change in density. Also, if you make, there was a question of partial volume effect. If you make a heating which is, let's say, that size, and you have a voxel size which is that size, I exaggerate, then you have a distribution of temperature. If you have a distribution of temperature, you're going to have a distribution of the phases inside your voxel. And you're making the net magnetization inside this voxel is the sum, the vectorial sum of all these magnetization having different orientations. And then you have to take care about the region that you're heating should be larger than your spatial resolution. In other words, you need to have sufficiently spatially resolved imaging to map the temperature change.
My question is, if we see a change of signal, so it can come from the change of temperature which is higher, and the change of the tissue due to the temperature?
Yes, if you're really changing the nature of the tissue, so you're burning it, probably you're going to change a number of parameters, and you may have you have to take care of that. Okay, is this a trick for researcher, or is this really a tool that is already in clinics? So the answer is the second. So this is an example of combining this HIFU system inside an MR. This is a platform developed by Philips, which goes also naive. And the idea that you can make temperature imaging. This is designed for the treatment of uterine fibroid. which is a non-malignant tumor. And then the idea is that you can make MR temperature imaging to monitor what you are doing while you are sending energy with your transducer. The nice thing about that is that you can burn the tissue without making surgery. Okay. And the idea there is that you can exploit, for example, instead of making these 4 points that I show, you can make concentric circles with your HIFU system. You can steer the focal point to make circles and then benefit from the progressive heating from the inside to the outside of this volume. Okay, it's an example. So this is the fibroid before, the fibroid during the treatment. So you can see that you can really, using this strategy, make quite a large heating. And then, once you have done the treatment, then you can, for example, inject a contrast agent and check that you have no perfusion inside your treated volume. Okay. People at Institut Langevin are really interested also in transskull therapy. So the idea would be to treat a tissue inside without making surgery. And the problem is that, well, the advantage from MR is MR in the brain is very easy because it's not moving and it provides quite a lot of signal to noise. And so this is an example of, I'm scanning from the left to right a brain of one of my students. So this is magnitude image, the phase image, and you can compute the temperature, the apparent temperature. Of course, there is no treatment here. You can see the standard deviation of the temperature, which is more or less the uncertainty of your measurement, which is in a range of, let's say, 1.5 degrees. So you can measure the temperature change with an uncertainty of in a range of 1 degree. Okay, with a spatial resolution, this one was, I think, 1.8 by 1.8 by 3 millimeter, and you can cover 20 slices over your brain every second, and you can do it even better. But the counterpart is that HIFU is difficult because you have the skull, and the skull is absorbing and distorting the emitted field by the transducer, and then you have something which is distorted, and then you don't have a very constructive interference here. So they have developed method to use a time reversal. So the first idea was to use a hydrophone that should be placed inside the brain, which is not really non-invasive. But just to show the principle, you have no brain air, but if you put hydrophone, then you emit a spherical wave. You register there what's the distorted wavefront, and then you return it, and you get a nice propagation, and you retrieve the energy that you wanted to have. This is one intensity, this is without correction, and it's 5% as compared to 100%. Okay, so this is how to use this in more practical ways. So the second idea was to use CT imaging. CT imaging, you can make a quantitative measurement, which is called the Hounsfield value, and you can use this and say that you have a kind of correlation between the speed of sound and the Hounsfield value, and then you can compute what will be your distorted front from the external part to then correct the phase on each element to retrieve the correct interference at the focus. So this is an example on monkey, and it has been proved to be working. And now it's also already used into the clinics, for example, for treatment of essential tremor. I wanted to continue to show you that you can also do this on mobile organ. Then it's really tricky because of motion. So motion, you need to do fast MRI, faster than motion. You need to develop strategies for compensating the influence of motion on your temperature imaging. Also developing strategy for HIFU. The problem also is that you have often quite large blood flow, which is a cooling effect, which is placed against you because you want to bring calories somewhere, and the blood flow is going to evacuate them. Can we measure that? And you have also the bones that absorb the tissue, and you can, if you do not take care, you can produce skin burns, and also reduces the acoustic intensity that you're delivering to your tissue. So, just an example. It's an example of the experiment we did a few years ago. This is a pig on the Sonolive system developed by Philips. So you have your transducer there, you have a water bath to ensure coupling of your HIFU toward your target. And using advanced MRI method, you can, for example, put one slice here, one slice here, one slice here, one vertical, if you want to see your net temperature heating in that direction. And for safety reason, because you are in the near field, you don't want to induce thermal injuries there. You can also put one slice here and make this. This can be updated with rapid imaging method every 400 milliseconds, meaning that you can get these 5 images more than 2 times a second, okay, with this image quality. Okay. And of course, you need to compensate for the motion because you cannot block the motion for minutes, and you want to do this under free breathing, or at least having a breathing activity. So this is an example I'm going to show. It's an example where you see the breathing. This is the liver, this is the gallbladder. And you see that the head is there, the tail is there. So the liver is moving with the respiration. And what we are doing, I'm going to explain you that you see it's blocked now. I'm going to explain you how it works. Technically, we did not block the breathing. It's still continuing to breathing. But what we do is that we are using the first images in a time series before we're hitting, and we measure the position of the liver at different states. Use this data as an atlas of reference, and then use this data to compensate for the images you acquire during the treatment. So by image processing, you can, play it again. So this is the learning phase, so use this information, and then you store that. This is at the beginning there. And using this, you can use this data to correct for the data that you acquire during the heating. So this is without correction on the temperature and with correction. So you can retrieve a very nice data. Okay? As I said before, the perfusion is playing against you. Can we model it? Yes, we can. So we use the Biot equation, which is a diffusion equation. This is the diffusivity, the perfusion, and the source energy, the absorption. What we did to test if this equation is valid is to use ex vivo kidney from a pig. You perfuse this kidney and you put this on top of a transducer inside the MR, and you make temperature energy. You're heating, then you see a temperature increase, and then a cooling, which is a combination of diffusion and perfusion. So can we retrieve these values? Yes. If you integrate over space for each time for your different slices, your temperature increase, then you can show that this does not depend anymore from the diffusion. And you can plot the accumulated energy at each time, and then you can model this. This is in red, the experiments, in black, the results from the fit from the equation I showed before, and you can retrieve the absorption coefficient and the perfusion. During the cooling period, it's going down because of perfusion, but also it's spread in time, so you can fit with the Gaussian function transform and plot the variance as a function of time. Theory says it's linear, and the experiment says it's linear, and using this you can retrieve the third value. So using this, simply the combination of 3D MR thermometry with non-invasive HIFU, you can predict what will be the answer of your tissue in terms of energy deposition. Okay, this shows that this absorption and diffusion do not depend on the flow that perfuses the kidney, but then if you vary the flow linearly, then you have the perfusion which is varying linearly with the flow which is expected. And you try to go as fast as you can. The bones. Bones is problematic, but then MRI can also help you. This is an example of an experiment I did a few years ago. I booked from the butcher a piece of a cartilage with bones. You have the bones there. The interspace there is the muscle in between the bones. You put that on top of transducer, a piece of liver, and then you can use images to segment the bones. Using this, you can project the shadow of your targeted point on the surface and transducer, and then switch off the elements or deactivate the elements that are in the shadow to avoid sending energy to the bones. Does this work? So you have an experiment there on the left. If you pay no attention, you use all the elements to emit. You're able to increase temperature there at the focal point, but then also around the bones, which is unwanted. And when you stop, it's decreasing there, but then since the bones is hitting very efficiently, it's going to continue to stay warm, and you have accumulated energy. If you not take care and switch off the elements that are in the shadow, you still get your temperature increase there, but you do not have any more temperature increase around your bones. Of course, the nice thing with MR is that you can use orthogonal plates going in direction. So at the same time, you can interleave vertical image with horizontal image. These two images are just below the bones here, and in these experiments, you can clearly see the temperature shadow from the bone. Okay? So, next point, I'm going to accelerate if I can. The problem is that we show I think yesterday someone said that the problem is that if you have a rupture in impedance, acoustic impedance, you may have troubles, you may have a reflection. And this may occur with ultrasound because you're sending quite a lot of energy. And for example, just behind a kidney, you have the bowels, which are not transmitting, and then you have reflection. And if you don't take care and send quite a lot of energy, yes, you can burn here where you want, but in the far field, you can also have a strong energy deposition or reflection, and you can maybe burn it. One of the ideas that was proposed is that you can, for example, change the acoustic properties of your tissue, for example, trying to make a boiling or cavitation by sending a short pulse with sufficient intensity. You need to change your properties of your tissue. And then when you're going afterwards to sonicate to make your temperature heating, then the acoustic field is going to be blocked or reflected there, so the energy is not going to spread after the focal point, but going to reflect it and increase the size there. Can we control that with a mount? Yes, this is different sequence, forget, don't be disturbed by that. What we simply add is simply a pair of gradients, okay, and what we do is that synchronize the ultrasound emission between one of the gradients. Using this, what we do is simply we encode in the phase of the signal the displacement, the push that we are creating with our ultrasound. This is what is shown here, so the transducer is below in the phase of my image. I can see and I can make a push that corresponds to where my tissue is displaced. I can do this for different acoustic power, and you have a nice linear curve, but above a certain threshold, then you're out from the linear domain. It's because then you have created something there, you have modified there something, and then you see that you have shifted down your maximum of displacement, and it's much larger. If you use this, calibrated with MR in situ at a given depth, then you can increase the temperature elevation. This is the same sonication done before modifying the tissue with this pulse that I've been calibrating with the MR-RF method. And afterwards, you see that you gain about 50% temperature increase above the basal temperature, which would be 37 degrees there. Using the same energy deposition, you simply create, without taking advantage of this effect, you simply make an hemorrhage, and using the same energy deposition, you can make a strong centimeter burn in 20 seconds. You can, of course, do both. So you can encode in the phase both the displacement and the temperature. How do you do that? You simply add a gradient in your encoding, and you synchronize your gradient there. And you simply change in successive acquisition the polarity of the gradient. So for one acquisition is going to be additive. Temperature, the phase due to temperature change is going to be added to the phase change to make push. And then the second one is going to be the difference. And by making simple processing sum and difference, you can retrieve temperature and displacement. The interesting thing of that is you can map simultaneously the temperature change in your tissue and your change in your elasticity or in your stiffness of your tissue. And you can, for example, use this second measurement, which is change in displacement, as a second value to see if you have a change in your tissue property. That was your question before. Okay, we did this on the brain, so maybe this would be of interest for Stéphane, for example, for that. So you can measure the temperature and the displacement simultaneously. And I want to finish in 2 minutes. I'm sorry, a bit long. Also, people are interested in working in rodents. This example, this is a mouse, which is a specific mouse. If you heat up this mouse in a given region, it's going to activate each protein that we all have in our body. But after this activation, it's going to code for a given gene, for example, a gene which is going to produce light that you can detect with bioluminescence device. But here the idea is that you need to heat sufficiently to induce this biological process to occur. But if you heat too much, you're going to destroy your tissue, and this is not going to occur. And you need to control your temperature change. It's going to be moderate. So ideally what you want to do is that you define a target temperature, and you want your temperature to follow this value. How do you do that? This was my first thing before. You can use standard automatic algorithm using the proportional integrative and derivative algorithm. But I want to show you that I can also use Fourier for that. That's something that we published about 15 years ago. You can rewrite your equation. Same one, I simply have no perfusion on this one. If you make a Fourier transformation over the spatial coordinates, you simply transfer this equation into a differential equation in the k-space, okay, k-space of temperature. And then you can integrate this value. This is the analytical form, and then of course you can express what will be the next, you want the next temperature to be a given value, and you can then use the actual value that you measure now, predict what will be the change due to diffusion, then include also the energy that you're going to deposit to compute what will be your next temperature. In other words, you can compute the forward you need to apply to have your next temperature to fit with what your actual temperature will evolve due to diffusion and depending on your source now. This is valid for ultrasound, but it's also valid for barbecue or for laser ablation. It's a general principle that's nothing specific with HYPERTHERMIA. It's an example where you can heat a mouse. This is our mouse 1 and 2. You make a moderate heating on the leg, and 6 hours after you put this animal under bioluminescence imaging, and you can clearly see the nice expression of the firefly luciferase, which shows that you're able to control the expression of the gene. Please think about that not as a tool for playing with mouse, but it's really a way of controlling the expression of the gene that is missing in a human body. I'm going to skip this. It was an example of what you can do also on the heart. And just to conclude, potential applications are goes from the small animals to large animals and of course to humans. There are already a number of devices existing for treating pathology in patients, but each time it's dedicated hardware for HIFU, specific MR imaging methods, therapeutic strategies, and also real-time imaging. So Fourier's contribution is, of course, in MR, also for image formation, also for temperature monitoring, for, as probably some of you or most of you know, that you have, for example, K-ray software, a package in MATLAB that allows to compute the propagation using Fourier, of the ultrasound waves using Fourier transformation. I show that you can also, briefly show that you can also use Fourier transformation to solve the Biot equation, also to make a control of temperature. And of course, you can also use Fourier in optics, it's well known. So, Bordeaux, for those who are not, we are here. Bordeaux is on the other side. It's a very nice city, also made of very old stone as Lyon. We have also some other interests with excellent point. And also, if you're interested in coming and say, please do it. So thank you. I'm sorry a bit long, but.
Very simple. How do you calibrate the temperature measurement?
Well, it has been done.
My question, how do you know inside? There is any way of knowing precisely that the MRI gives the right temperature? I
understand. You can use, for example, optic sensors that are optic thermometers that are invasive. You can put it for calibration purpose at the beginning. You can do that. And we did that, and we see a very good correlation, a very good correspondence between your temperature measurement that you get from MR and from your device, which is implanted.
So you use a kind of something that really gives you the temperature.
You can do that, but it's not the idea. This is the idea to calibrate. Once you have calibrated, the idea is to insert nothing into your patient.
And the second question is more simple.
Oh, this one was okay.
Why not, as you are expert in MRI, why you are not using MRI or the magnetic field to do hypothermia by using iron oxide particles? Because now it's
hyperthermia or hypothermia?
Hyperthermia.
Yes, that's technically feasible.
Because you can avoid IFO and then go directly.
Yeah, for sure. All this thermometry stuff has nothing specific to HIFU. This can be done. I've done that on the liver with optic fiber years ago. You can do that. I've done that with radiofrequency ablation with HIFU. So I focus this on HIFU because it's ultrasound meeting. But yeah, sure, you could also make this inductive heating. That's technically feasible. You have to take care that you're bringing also an oscillating magnet into a magnet. So maybe technically this is a challenge because it's a confined space, and you have to be sure that the instrumentation you bring inside is not going to disturb your image quality.
The only problem is injecting the iron oxide inside the brain, for example. But there is a moving field now on this.
Yeah, for sure.
Okay, a very last question before the aperitif time. So,
I see. I understand now.
Is it possible to have an idea about the complexity of the algorithm?
Of the complexity of?
The algorithm that is used in the job temperature.
It's a different. If you have something static, a mobile organ, you take the MR image before, you take the phase of this image, you take the phase of the image that you acquire during the heating, and you make a simple pixel by pixel difference. This is one line of code. This is the difference. And you have a multiplying factor. Of course, then you have to take care if you have phase wraps, for example. This morning we had a discussion about a special phase wrap. You can use that, but we prefer, as we have temperature changing time and we know that it's going to affect the phase, we use a temporary phase wrap. We don't use a special phase wrap. Does this answer your question?
thank you again, Bruno.